So here's the second part of the lecture, the B part. Here's the Colorado PHET simulation. This is the simulation that's I've set up to simulate exactly that multiple choice qualitative question that I did in the first part of the lecture. The question was if you have a circuit like this and change the value of the resistance, what happens to the peak current and what happens to the time of the timeline of the current change. It's 2 o'clock in the morning. I'm tired. So here, this is set up to do it. I've got a battery, a switch, a resistor, an inductor, and a voltage across the inductor is read here, and the current through the circuit elements is shown there. So this is with the resistance value set to 30 ohms. Okay, so watch what happens when I close the switch. This current comes up to about the voltage comes up to about the 9 volts, and the current comes up to zero point 0.3 amps in a kind of a reasonable time, reasonably slow time. So I'm going to open the switch, reset the dynamics, change the value of the resistance. We'll change it from 30 to 90. Okay, and the prediction of the equations and the physical reasoning is that the peak current is going to be smaller and it'll take less time to get there. Is that true? Uh, Hopefully, yes, if the physics works. So, sure enough, the timeline is much shorter, it's quicker, and the current is less. So, that makes sense. And that makes sense in terms of the Faraday's law here. I open the switch, and that voltage going crazy is actually a physical effect because there's a huge L didt from this inductor here, so I have to reset the dynamics. I'm going to pause the simulation now and replace it with an LC circuit. So let me pause this so I don't waste your time looking at me build a new circuit. So here we go. How do I do this? Oh yeah, I go up here and I'm going to pause this. With any luck, this will work. So here's the same circuit with an LC circuit. Here's it. I'm going to kill this. Start over again. Pause. So here now is the LC circuit. Got rid of the resistor and changed this configuration. So we're going to charge this capacitor. You can see the voltage jump up to the full battery voltage here. Let me increase the scale there. No, I keep it down there. So there's the battery voltage. I open that switch. Okay, I'm going to open this. Whoops. Open that switch, and I'm going to close this switch and watch what happens then. Okay. The voltage comes down. You can see the charge building up, plus and minus on the capacitor. You can see the voltage swinging positive and negative, and you can see the electrons opposite to the conventional current flowing back and forth like that. Let me try and walk you through the timeline here. Let me catch this at close to zero voltage. Here the battery has, here's the capacitor has zero voltage on it. Okay, at zero voltage, the current is maximum. Okay, and then we single step it. The voltage goes to zero exactly right there. Okay, at that point, the current over here is maximum. Here we have zero stored energy in the electric field and maximum current flow over here. So zero energy in the electric field, maximum energy in the magnetic field. We single step some more. The charge flowing from the inductor starts to recharge the capacitor. Eventually, when the capacitor is at full voltage, which is about here, full negative voltage, at that point, you see the current in the inductor goes to zero. So kind of hard to see that. Let me let the simulation run. Watch when this is maximum, this is zero. When this is zero, this is maximum flow. You have to watch the pictorial here and the flow of the electrons. So there it is. Maximum flow there and back and forth changing directions. I'm saying that's wrong, but you get the idea. Uh, that's enough of that. Good night, folks. It's 2 o'clock in the morning. Adios.